I kind of know, guys. This stuff is taxing to the brain, but you know what? I think you might even say, oh my gosh, this is actually kind of fun because here's the good news. This doesn't actually really involve any math. So that's kind of a nice thing. Okay, I have to switch the way I'm sitting. It's because my legs are like falling asleep. Sitting on this funky couch that we have here and trying to block out that light with my head so you don't have like this light flare behind me. Okay, so we're going to learn how to, the next section is called building atoms in the quantum mechanical model. We're going to build atoms. When we say build atoms, we're going to build the model for each of these different elements. So one important thing to remember is that, they say, first of all forms of matter try to stay in their lowest possible energy state. And they use the analogy matter's lazy. I mean, matter's not lazy. This is just more of an energy kind of thing. It's a nice way to think about it, though, to help you remember that matter doesn't want to work harder than it needs to, like most anything. And it always tries to stay in its lowest energy configuration. So if you remember that light that was when Bohr was heating those different elements with electricity, that those electrons got excited and they moved to a farther away energy level, but then eventually they wanted to move back to their lower energy state, and so they would give off energy, which you saw as light, or which was seen as light, and they went back to a lower energy state. And the why do they go back to those lower energy levels? It's just the nature of matter to want to be in its lowest energy state. We'd have to ask God as to why, but mostly because if you need energy, then that has to be sustained. So they're going to go to their lowest energy that they just have on their own. I guess, don't take that too much. That's me trying to offer a why that was not in the book. So that don't even take too much account to what I just said on that part. But they do want to be in their lowest energy state. So, and that's even given a name because it's so significant. It's the lowest possible energy state for a given substance is called its ground state. And that's different for every substance on Earth. Okay, so given all that, we are going to build some configuration. So here's something I want you to do first. Okay, so you're going to take out your periodic table, and you're going to look at page, and make sure you do this because you can use it on the test, and you will kick yourself if you don't do it, because this will be doable, but I think more confusing. This would be very helpful if you write it down. It's super doable if you don't, but I think it'd be kind of foolish not to have a little more help. You're going to see on page 120 something that says S block, P block, D block, F block. Hopefully that sounds like something familiar based on what we've been talking about. And so what I want you to do, and be careful you don't copy over your atomic number. Sorry, left and right reverses. It's like trying to drive in reverse. And I think I'm doing one thing and it's not doing what I want to do. Stop it. Okay, so you're just going to copy what they have here. So you'll see there's that S block, and it's basically like those first two columns there. And you can outline that and put S block. But the S block also captures that one little square over there. So you can outline those and write S block above it. And then P block is going to be right over here. So you're going to, don't go exactly with what I write, but it's like that whole, it's like really hard to do when you're not looking at what you're doing. That's that whole P block. And then the D block is basically right in there, all those yellow. And I actually wrote in, okay, so LA is number 57. And the way this works on here is number 57 is actually in that block. And number 89 is actually in that block. So you could just write those in. Probably won't go that far, but it's good to know. Okay, these are just constructs, okay, to make the task that we're going to do easier. So pause the video. Everybody get a Sharpie marker or a pen and write that in before we go, because you're going to want that on your actual table that you're using. And while you're at it, if you look up above there, ours doesn't have this, and you can add it in. You'll see like 1A above this first column, and then 2A, and then 3B, 4B, 5B. Go ahead and write those in above there too. Just label that on your chart as well. Okay. So pause the video, write that all down, make sure everybody's got that in there well, and then move on. Right. What that is telling us, the S block, P block, is that the periodic table is arranged based on these orbital shapes and energy levels and where everything falls. based on, so it doesn't just go all S and then all P, because we can have like a like a three, what did I say, like the 3D that can get filled before the 4S. And so the periodic table is going to help us sort that out as to what that looks like. So let's just do an example. Let me get out my whiteboard here. They give us an example of write the electron configuration for a carbon atom. Okay, so we look for carbon on the periodic table. And so we know that it's number 6, right? Carbon's an easy one. You probably have it memorized here. Carbon has that atomic number 6. Do you remember what that tells us? It tells us that it has 6 protons and has the same number of protons or electrons as it does protons, so it has 6 electrons. So I want to see where those electrons all fall, which energy levels they fall in. So the way I'm writing this down, I'm just going to write down carbon to remind us what we're working on here, okay? And so the first thing I look at is 1s, first energy level S, and 2 electrons can fill that orbital. So I just write down 1s2, just like that, okay? 2 electrons are filling the first energy level in the S-shaped orbital. And if you see that, this is 1s, this is 1s1, this is 1s2. If I were writing the electron shape for hydrogen, it would just be 1s1. It only has that 1 electron. And if I were writing it for helium, it would be 1s2, and then that orbital would be full. And then when I go down to the next lithium, and I look and say, this is going to be starting, I'm still in S block, right? This is still the S block. But now, and you can write, if you want to label also, this might help you, but you could write just 1, so you know what, just to help you keep track of what row you're in. That actually probably be quite helpful. 6. You'll just have to make one adjustment with the d orbitals, but you see how I did that there on the side, just so you know which one you're in. Okay, we're going to work a couple of these, so do not panic if you're like, what are we doing? What is she talking about? Don't panic, okay? Just try to follow it. Just try to flow with it, and it'll make sense, I promise. It's going to make sense. I guess I can't promise that, but I think if you keep at it, it will make sense to you. Okay, so we filled 1s2, and then we come to the next row. We're always just going to go down a row and come to the next row. Okay, so now I have second energy level. This is like my energy levels here. And I'm in the S block, so I have 2, 2s1, and 2s2. That whole orbital can get filled. I haven't gotten, if you want to look at it this way, I've only used up 4 electrons so far. I still have more to go. 2s2, and I come over here. I'm still in the second energy level, but now I'm in the P block. And I'm going to write 2p, so I'm in the P block, the second energy level. But here's carbon right here, right? So there's 1 electron, 2 electrons. So I'm only going to write 2p2. Now, remember, in this P block, there are 3 orbitals that can each hold 2 electrons. So look, 1, 2, 3, 4, 5, 6. It's like magic. There are all the possible electrons that can fit in that P level. But if I'm only going to carbon, sorry, I can't see where I'm pointing. If I'm only going to carbon, there's only 2 electrons there that need to get into something. And so I'm only going to be in the second energy level, and only 2 of those p orbitals are going to have electrons. Now, you might ask me, well, is it the horizontal p or the vertical p? I have no idea, and I don't even know if it's possible to know. If you're super interested, I will find out from somebody smarter than me. I will probably email my old physics professor or chemistry. I used to be friends with my old physics professor on Facebook. He would probably know. I can't even remember my old chemistry professor's name, but I will find out for you. If you really care to know, we can find out. I don't know, but we just know at least 2 of those orbitals are filled. One of those orbitals is filled with 2 electrons. Okay, so that right there is carbon's electron configuration. Those are the words for that, electron configuration. How the electrons are configured around the nucleus. Okay? that's really like that concept is as complicated as this gets. Now, we're going to go farther. We're going to do another one, and we're going to move farther into the chart so you can see how to read the periodic table as you do this. But the concept of it is only as complicated as that. Okay, so let's do another one. Let's do chlorine. I'm just doing the examples that they have so you can see it in the book, see me do it, and then we'll do some that they don't show. Okay, so chlorine. So I'm just going to start out the same way. So you can, sometimes I kind of try to find it on the periodic table so I know where I'm headed. Are you going to tell me something? This is super exciting stuff that I'm doing here. Like, do you want to watch electron configuration for chlorine? This is on video, so if you're going to tell me something personal, huh?
I was looking at your flight.
Oh, great. Did they go down?
One of his
Oh,
people higher up told him about this app.
nice. But be careful. It might be one of those things where once you look at it once, then the price keeps going up or something. So save a device that you haven't looked at it on when you're going to actually buy it. Okay, so if we look at chlorine, I like to just find it on the chart so I can see. Don't go to sleep on the computer. So I can see where I'm heading. So, chlorine's right down here. So I'm going to start out the same way. I've got my first energy level, and those are both filled because I got to get all the way down here. So I'm just going to write 1s2. Those 2 electrons jump into the first energy level, into the s orbital, and then I go down to the second energy level, and I go to 2s2. Those are both going to fill up. Now I'm going to go to second energy level, p orbitals, because I'm in the p block, right? So I have all 6 are filled up because I haven't gotten down to chlorine yet. So I'm going to write in 2p6. So look, I've used 6, 7, 8, 9, 10. Chlorine has 17. I haven't used them all up yet. Now I go from the second energy down to the third level. Okay, I'm back to S. So now those electrons are jumping into the third energy level, s orbitals. I've got 2 there. What?
This stuff isn't that
No, I want you to hear it and try it. It's not too bad, right?
bad.
Delaney says it's not that bad.
I actually like this part.
And she said she actually liked that. And I'm telling you that is saying something because Delaney does not love science.
Part I liked.
It really is actually kind of fun once you get the hang of it. Because it's not, you don't really have to expend that much thought. So 3s2, that gets all the way filled up.
Thank you.
I don't care, it's fine. And then I jump over to the 3. I'm still in the third energy level. That is Delaney saying hi to. Third energy level. And I'm going to use 1, 2, 3, 4, 5. Sorry, you can't see where I'm counting. 5 electrons to count over to chlorine. So I just have 3p5. That 6th one for argon isn't filled yet. Okay, and we're going to talk about this 8A that it's labeled, that column's kind of special. And we'll find out more why in module. You might be beginning to form some idea of why, maybe, if you're intuitive about chemistry. Okay, so that is chlorine's electron configuration. Okay, not too bad, right? Maybe I built this up and made you sound like it was going to be so much harder. I should have been this piece of cake. No, I don't want you to feel like if it's hard for you that it's a piece of cake. It's a piece of cake because I've looked at it. And I've seen it once before when I was younger, and then I review it when I'm old. I saw it with Mrs. Estes a couple years ago. So of course it feels easy to me, but it might not be feeling that way to you, and that is okay, but I think it will eventually. All right, so let's start over here because this one's kind of long. What is Ag? I remember. Oh, silver. I should know that. Hello. Okay, so electron configuration for Ag. So we're going to have to go pretty far, right? Ag is all the way down here, so we can start out quick. I'm going to go a little faster. 1s2 is filled. 1s2 is filled. 2s2 is filled. 2p6 is filled. Jump down to the third. 3s2. 3p6. 3p6. And I jump down to here. 4s2. Okay, here's where we're going to get just a little tricky, okay? Not super tricky, actually. It's not really even tricky. You just have to remember something. Now be careful. This says 4. We feel like we're in the 4th energy level. But do you remember where d orbitals start? They don't exist in the 2nd energy level. And we're just starting with d orbitals here. They start in the 3rd energy level. So this first row of d is actually the 3rd energy level. Okay, so you have to remember where. So they say, oh, just take whatever energy level you're on and subtract 1 once you start with D. You can do it that way, or you can just remember, okay, D starts with 3, and I don't even care if you want to put like 3, 4, 5, 6 down there. Because honestly, I think you still have to understand what you're doing to get it right. So, and you might get a question like, which energy level do d orbitals start in? And you just need to know in your brain that that's where they start. So I go from 4s2 to 3d, and let's see how many. Do all 10 get used? Yes, because I haven't gotten down to silver yet down here. So it's 3d10. And then I go back to, okay, but be careful. When you come back to the P here, sorry, let me move this. There, that's probably so much better. I should have moved that. You don't need to see my face. You just need to see this periodic table. When I come back over to P here, I was in 3D, but this is back to matching this. This is still actually the 4th energy level for P, and they're all filled. So it's, you can just come down to the next line. They don't have to go in a line. I mean, go in order, but you can make a second line. So that's 4P10. No, 6. Oh, sorry, I'm not in D. 4P6. 4P6. Then I jump down to the 5th energy level, 5s2. But this is actually 4D. Okay, now we're on the line where silver's at. So we're going to use, let's write down 4D. So remember where we're at. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, it's 49. Let me make sure mine matches the book. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 49. Good, I got it right. I'm glad. It'd be really bad if I messed you up. Okay, so that's awesome, right? Now, let's learn a little trick so we don't, when they're really long, like, oh, that could take you a while if you're down here at like whatever this is, borium or hassium or any of those. It's going to take a while, right? There's a lot to write out. There's a nice little abbreviation you can do. So remember I was saying that this column 8 is kind of special, and you're going to find out why. It has to do with being like complete, with orbitals being full and being very stable, okay? These are very stable substances, the noble gases, okay? We'll learn more about those. But what we can do is we can use those as an abbreviation. Let me just show you an example, and I think it'll make sense. Let's say I want to find, what is the example they give? The first one's real easy. They want you to find strontium, SR, number 38 here. Okay, so what I can do is I can find the noble gas right before it. So if I'm on 5, if I go back to 4, I can take krypton and I can write it down and I can put brackets. And I'm saying that is the abbreviation for the electron configuration up until krypton, instead of writing out all the 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 3p6. Okay, that would have, that's what I've encapsulated by writing down krypton in brackets. So I start here and then I pick back up on 5 and I say 5s2. And look, I'm in strontium. It right there, it fills up the 2 electrons for that 5th energy s orbital. Try to say those words. Be able to describe what you're doing there. I've put 2 electrons and the s orbital in the 5th energy level. That will help you know if you actually understand what you're doing or you understand what these things are all about. So that is an abbreviation for the strontium electron configuration. Okay, let's do a more complicated one. Same idea. We'll do it for selenium. So selenium is where? I should know faster. Right down here, number 34. Okay, so I look for the one right before it, which would be argon. And so I just put argon in brackets. Make sure you put it in brackets. That's to tell your person you're communicating with that that's what you're doing. And so I'm here. I'm going to jump down to the 4s2 and write that next. 2 electrons on the 4th energy level in this s orbital. Now I get down to D, but right, I'm in the 3rd energy level, so it's 3d10. They're all filled. Where am I going again? Oh yeah, selenium. 3d10. And then I get back over to the 4th, because this is 2, 3, 4. 4th level for P. And 1, 2, 3, 4 of them are used. So I just put in 4. So does that look right? 4s2, 3d10, 4b4. Good. It's always good when it matches the book. Okay, so that's how you can use those abbreviations. You can only use the noble gas. You can't just pick some random one in here. You have to use the noble the noble gases here is of what you abbreviate. Okay? I think that they have a really lovely discussion of the amazing design of atoms. And if you have not already come to that conclusion yourself, which actually it's really hard for me to understand how I think it's harder to believe that any of that could just occur randomly, or actually, when you think about it, all of those atoms and the way they work together have to be exactly right. Like there can't be any in-betweens where a proton and electrons charges don't exactly cancel each other out, or everything has to be in such a delicate balance that trying to make an argument for evolution to then get to that really seems hard to believe to me. I just don't even actually find that possible to picture how that would actually work. I don't know how you feel about evolution versus other things. I think there can be evolution of a species to become stronger, but that's different than a whole entire like things being created, like different atoms or different substances or different elements. So anyway, there's just a discussion about the amazing design of atoms and how that's sort of like the part of that general revelation. Do you remember that from, if you run into that, there's God's general revelation and his specific revelation. So when he makes a specific revelation, he's specifically talking to a person, like when he talks to Moses from a burning bush. But God's general revelation is available to everybody. And sometimes we talk about that in terms of just the beauty of creation and magnificence of mountains and all these cool things, the oceans that God's created that you can just sit in awe of. But even we often talk about big things, but when you look at the design of these microscopic atoms, that also is part of God's general revelation, the beauty and intricacy and just absolute wonder of how these atoms are designed. It's pretty amazing, actually. I mean, just think, like in your body right now, in this couch, in this, everything around me are these atoms and these electrons spinning around and jumping to these different energy levels, and it's phenomenal. It's pretty phenomenal. So good essay at the end there, just kind of pointing that and more specific than what I've been talking about. So check it out. Okay, that's the end of Module 3. Okay, so I really would encourage you to maybe try these together, try a few together, see if you're all coming up with the same answers. We could do some more together, and I might in a different video, but I'll probably end this one here for now. And I would encourage you in class to try some of these, see if you get the same answers. If you're not, try and come to a consensus of where you're getting messed up. If everybody gets stuck on the same thing, make sure you're marking that down and sending it to me so I can quick say, hey, this is how you would do it. Because even while I'm gone, I'll have Wi-Fi in different places, and I could quick make a video, maybe our time, because the time zone, it's like an 8-hour difference for the most part when I'm in Dubai. And then when I'm in Portugal, it's a little less. It's maybe 6 hours or 4 hours. No, it's probably like a 6-hour difference. Whatever. The time zones aren't going to always match up for us to communicate, but if I know you're struggling with a certain problem, I can make a quick video. Hey, here's how you do it. Grab a piece of paper, write it out, show you, and send it off to everyone so you can see that with me actually talking through it. Okay, so let's have lots of good communication about where you're stuck and where you need more help. Okay? All right, that's it for now. Bye, guys.